Hello and welcome to another episode of the Clojure Pills screencast. This is episode 15 and we're going to talk about contains ? In the standard library. First of all, just remembering that the content of the screencast is roughly based on the content of the book I'm writing for mining called the Clojure Standard Library, an annotated guide. I have here for you a 42% discount code on at checkout, and if you use the code on display on the slide, you can find the book at the link below, and you can get in touch with me with my Twitter handle at reborg for any questions. So let's get started. Contains is a simple function. It tells us if a key is present in a collection, and here I'm reporting the entire docstring, which is perfectly clear about what contains do and what it cannot do. Still, it requires probably some explanation. So first of all, the definition of a key, because it depends on the kind of collection you're using contains on. And then if we move on in the explanation, you can see that if you have numerical indexed collections, like vectors, for example, or native arrays, we are using key as one of the index in the vector to test if the index is present, and therefore if an element is present at that index. Contains promise you that it's going to operate at constant or logarithmic time. And particularly, it will not perform a linear search. So we can already imagine that contains is not going to work on sequences and lists and sequential collections in general. Okay, some example to explain how contains work. So normal use, sorry, it's a little bit off the screen. Normal use of contains is, for example, with maps, we can clearly see if a key is present in a map, and keyword B, for example, is present in the map. If we try to see if a value is present in the map, so contains is not for you, because the key, the second parameter needs to be one of the key in the map, or is interpreted as such when you use it on a map. You can also use it on sets with roughly the same meaning, so you can check if an element is present in a set, and in this case the key is considered like one of the elements in the set. And I have a little question now for you. So knowing that records are like implements map semantic, what do you think this is going to print? So we have a definition of a record with 3 fields, X, Y, and Z, and we create an instance of that record, and the record looks like this, roughly like a map, that is a record. So contains works on record. What do you think is going to print when we try to see if the number 1 is present in the record? So if you remember the meaning of searching, the meaning of key for maps, this is returning false, because contains is not telling you if the value is present in the record, it's telling you if the key is present in the record. And the number 1 is not present, the key X is instead. Less common use is with vectors, where it's also generating some confusion, especially for beginners, because contains of the element 1 in a vector containing 3 keywords ABC should clearly be false, but this is, I repeat, this is a vector is an indexed collection, so it's got numbers at each index starting from 0, so A is 0, B is 1, B is 1, C is 2. So what we are asking here is if index 1 is present in the vector, which it is. So it's returning true. And this case is on strings, and strings are considered indexed collections, similar to vector. And this is asking if the index 4 is present in the string, not if the number 4 is in the string, so it's going to be false, because 0, 1, 2, 3 is 0 based, so the index 4 is not present. For working in indexed collections, one requirement is that the second parameter you pass, the key, must be a number. So if you don't pass a number, like in this case, is returning false, but it's not returning false because the element is not in the vector or the index is not in the vector. It's always going to return false as error, so it's not going to work. And it needs to be a number, and it also needs to be a number below 2 to the power of 32, which is like 32 bits, is the size of Java arrays. And we can see what happens if we try to see if an element is present at that large index. So power of 2 to the power of 32 is like a relatively big number, is quite big, not impossible to find in real life. If you try to see if that number is present in this vector, you will surprisingly see that it is present. And the reason is that when you look at that big number as an integer value, is going to be truncated and is going to lose precision, so is rolling back to the beginning of integers in terms of bits, and is returning 0. And that's why contains is returning true in this case. So it is quite a corner case, something to remember, probably not very common. So in terms of instead of what are common use cases of contains, one is to verify if nil is present in a collection. So you can see that contains is working with nil, it's telling you that nil is present in this set, there are no problems. It wouldn't work if you just use the set as a function, as idiomatically is done in many other cases, but when it returns nils is ambiguous because you cannot know, you don't know if it's returning nil because the element is not present or because it's nil that is present. So you don't know. So in this case, it's good to use contains. And as an extended example, I have like a network of sensors that is connected to some central location, central point, and we are reading from that central location. And we read each sensor if the sensor has problems. And instead of returning a correct status like this one, nicely wrapped in a map, is returning nil. What we want for this specific example is a way to tell if all the sensors are working correctly. So we don't want to filter them out. We want to effectively see if there are wrong readings or malfunctioning sensors. So this sounds like a good use case for containers. And we can prepare predicate problems that is taking the readings of the sensors and is putting the sensors inside a set and then verify if the nil is present in this set. So it cannot, we need to move the sensors from a vector into a set because it wouldn't work with a vector because the meaning of key would be different. We really want to see if the nil is present in the vector, so we move it into a set. And we just prepare a little helper here that is raising when there are problems with the sensors, it's raising an exception. So if we evaluate all of this, there we go. Then we can try it out, raise on error with the sensor read, and you can see that it's correctly picking up the presence of a nil and is returning a malfunctioning sensor. You can also have a look at sum. Sum is an idiomatic way to verify if an element is present in a vector. So in this case, we are not forced to use an integer index. We can use a keyword. We need to wrap it in a set, and then we can use sum to see if the keyword A is present in this vector. And it's not returning true, it's returning the keyword itself or nil. So, sorry, it suffers from the problem of ambiguity with nils. So if you search for something that is not in the array, it's going to return nil. But if you search for actually nil in the array, you don't know if this is working or not. There's also Java interrupt contains. Contains works exactly as expected. Dot contains. It verifies if the keyword C, or like this key, is present in the vector as an element, as you probably might expect. There's also a nice feature on strings from the Java version of contains, which is verifying if a substring is present in a string. So that might be useful, and is a single liner to see if a substring is present. We can now have a look at the implementation details. So if we check, right. There we go. So if we go, nothing to get into contains, let me make it bigger. Sorry, a little bit of a cold this time. If we go inside the contains implementation, you can see it's a very simple function in the Clojure side of things. It's all implemented on the Java side. It's calling into the RT, runtime class. And if we now go into the runtime class, we can see that contains is a cascading conditional on the type of the collection, and is taking different routes depending on the type of the collection. So if you get an associative thing like a map or a vector, it goes into contains K. If you have a persistent set, it goes into contains. If you have a Java map, it goes here. A Java set, it goes here. And if you have instead a number as a key with something that is either a string or an array, is getting into this implementation, which at the end of the day is just counting and is verifying if the index you're passing in is below the count of the collection. So basically the performance profile is going to be dependent on the type of the collection. I prepared a little chart to summarize that, and we can see contains used against different type of collections, and these collections are of different sizes. We start from 100 and we go up to 1 million items. As expected, sorted collections are slightly slower. You need to reach into the element to verify if the element is present, following like the binary tree, so verifying at each node which side of the tree you need to get, right or left. So it's taking a little more time, and it's also the case of logarithmic, big O of log n performance profile. So it's logarithmic, which is a very low way of increasing, so it's not going to be a problem 99% of the time. As you can see, with 1 million items, we are around 300 nanoseconds. It's still very fast, so it's not probably going to be a problem. But the promise of contains is maintained if you look at the other kind of collections. For sets, maps, records, or vectors, is a constant time access. It's also quite fast. So promise maintained is not going to work on sequences, but it's going to work very fast on indexed collections and associative data structures. So I think this is all I want to say about contains. You can find the show notes, including the REPL examples that I've been showing in the screencast, at the link at the bottom of this slide. So that was all for today. I hope you have a good time, and until next time, goodbye.